In this video, I'll cover sections 1 and 2 of Chapter 10. Chapter 10 starts our analysis of multiple variables at the same time. So for this video, we're going to begin to learn the difference between independence and paired samples. We'll discuss independent samples in this video. And we'll also learn about confidence intervals and hypothesis tests for two means using those independent samples. So what does it mean for samples to be independent? It means those samples are selected from two or more populations in such a way that the occurrence of the values from one sample do not influence the probability of the occurrence of the values in another sample. So this is just the way we defined independent back in Chapter 4. We're going to talk about estimating these two population means and comparing them with the standard deviations of both of those known and those population standard deviations unknown, much like the techniques we've used in other chapters. So we're going to have to make the assumptions that we've made in previous chapters so that we can do our analyses. That assumption is that our population is normally distributed or that our sample size is at least 30. Those two things allow us to have a normally distributed sampling distribution. Now we're going to focus on the case of two independent samples and assume that we know the true population standard deviation for each of those populations. To see if two population means are different from each other, we look at the difference between the sample means. So the best point estimate for us to talk about the difference between the true population means is the sample mean from the first minus the sample mean from the second. And if those true population standard deviations are known, our standard deviation of the sampling distribution for the difference between the means is the square root of the first standard deviation squared, or the variance, divided by our sample size, plus the second standard deviation squared over our second sample size. Remember, the standard deviation squared is just the variance. So we can calculate a confidence interval for our estimate of the difference between population means, given the true standard deviations from those populations. The confidence interval that estimates the difference between the true population means is really just that point estimate, so the difference between our sample means, plus or minus a z-critical value, this would be just like what we've calculated in previous chapters, times that standard error that we just talked about in the last slide. Let's run through an example of this. So suppose that we're interested in estimating the difference in the average time that male and female customers spend per visit at a fitness center. Previous studies indicate that the true population standard deviation of males is 11 minutes and that of females is 16 minutes. We have a sample of 100 of each gender, and that shows that the average time that men spend in the gym is 42.4 minutes, while females spend on average 34.5 minutes. Let's create a 95% confidence interval to describe for us the difference between the true population means. So we're going to do the sample mean of male minus female, plus or minus a z-critical value associated with a 95% confidence level, times the standard error, which would be the variance for male divided by the sample size for male, plus the variance for female divided by the sample size for female. So plug in what we know. Men spent on average 42.4 minutes in the sample and 34.5 minutes for females. Our z-critical value for a 95% confidence interval is 1.96. Our standard deviation was 11 for men, so we put in 11 squared, 16 for women, so 16 squared, and each of those had a sample size of 100. As we simplify this, we see the difference between the two sample means is 7.9 minutes. The margin of error is plus or minus 3.8 minutes. We're 95% confident that the mean distance in time spent in fitness centers between men and women is 4.09 minutes and 11.71 minutes. Now let's consider the case where we do not know the true population standard deviations. We still have to have that the populations are normally distributed, or at least that n is greater than or equal to 30. We'll start off by assuming that the two populations have approximately equal variances, and we'll continue the assumption that the samples are independent. Since the population standard deviations are assumed equal, we'll use those two sample standard deviations and pool them to estimate the sampling distribution's standard deviation. The t-critical value comes from the t-distribution, with n1 plus n2 minus 2 degrees of freedom. So we calculate the standard deviation as follows. S sub p, p means pooled. This S is because we're using sample standard deviations to replace our sigma, our true population standard deviation. So we do n1 minus 1 times S1 squared plus n2 minus 1 times S2 squared divided by those new degrees of freedom that we have. Square root of that to turn that into a standard deviation. In order to calculate the confidence interval, we still take our point estimate, but because we don't know the true population standard deviations, we use a t-critical value. And again, that t-critical value has n1 plus n2 minus 2 degrees of freedom. Then we have our pooled standard deviation times the square root of 1 over the sample sizes added together. Now we're going to have Minitab actually calculate this for us, but this is what's going on behind the scenes. We just considered the case where the two standard deviations are not known and they were equal. What if they're not equal? If they're not equal, then we're not going to pool those two sample standard deviations. Instead, we'll calculate it much like we did when we had the true standard deviations known. So we've got our point estimate plus or minus a t-critical because we don't know the true population standard deviations, and that's introduced that extra uncertainty. And we'll multiply by the square root of S1 squared over N1 plus S2 squared over N2. The degrees of freedom get really complicated here. If we're going to do a confidence interval or a hypothesis test with the two sigmas being unknown and not equal, it's much easier to use our software and to use the p-value test for any kind of hypothesis test that we might want to do. Minitab can calculate this confidence interval for us. We want to be able to perform hypothesis tests also when we're talking about two means. We might want to be able to say that mean 1 is less than mean 2. To be able to prove that, we need to form a hypothesis test and conduct that. So we might be interested in proving that the population mean from the first population is less than the population mean from the second population, which means we'll assume the opposite. That's really the same as saying that mean 1 minus mean 2 is less than 0. If the first mean is smaller than the second mean, then the difference between those two means would be less than 0. So when we actually perform the hypothesis test in the computer, this is what's actually being tested. In our brains, we're really thinking that mean 1 is less than mean 2 if we reject the null hypothesis. This would be considered a lower tail test. So the first mean would need to be so far below the second mean that the difference is way below 0. And when I say way below 0, I mean statistically below 0. We could have an upper tail test. We may want to prove that the mean of the first population is greater than the mean of the second population. That would mean that the first mean is statistically bigger than the second mean, so mu1 minus mu2 would have to be statistically greater than 0. Or we can do a two-tail test. We don't care if one's greater or less than, we just want to show that these two means are statistically different from each other. To be statistically different from each other, the difference between the two means would have to be something other than 0. So we have the same kind of thing here that we've seen in several chapters. If we know our true population standard deviation, we can use a z-test. And we'll use that standard deviation that we saw a moment ago associated with the confidence interval that allowed us to use the z. If the true standard deviations are not known but assumed equal, we have to use a t-critical value, and we'll calculate a t-test statistic using that pooled standard deviation and n1 plus n2 minus 2 degrees of freedom. If those two standard deviations are not known and not assumed equal, then we'll have to use S1 and S2 to estimate our standard deviation, and we'll still use a t-test statistic and a t-critical value. So our test statistic, or our z-score, if we know the true population standard deviations, is the point estimate, so x bar 1 minus x bar 2, minus the hypothesized mean difference. So the mean difference that we assume in our null hypothesis between mu1 and mu2, divided by our standard error when we know the true population standard deviations. So sigma 1 squared over n1 plus sigma 2 squared over n2. If the true population standard deviations are not known but assumed equal, we can use that pooled standard deviation times the square root of the 1 over the sample sizes added together. Our point estimate is still x bar 1 minus x bar 2 minus our hypothesized mean difference. So the only thing that really changed when we went from our standard deviations not being known to being known is the fact that we had to use this pooled standard deviation on the bottom, and that turns out to require us to use a t-score and a t-critical to compare. If those true population standard deviations are unknown and assumed not equal, we'll still do our point estimate minus the hypothesized mean difference, and then divided by that standard error that we saw in this case before when we were doing the confidence interval. The sample standard deviation for the first squared divided by the sample size, plus the sample standard deviation for the second squared divided by that sample size. Now we're fortunate that we use Minitab because it will calculate the t or z scores for us, so we won't have to calculate those. It will not provide us the t or z critical values. However, Excel could do that. We could also do these hypothesis tests using the p-value approach that we've seen in previous chapters. So suppose we're interested in doing this hypothesis test for the means. A lower tail test would look just like a lower tail test for a single population mean. In this case, we're looking for the mean difference between the two to be something statistically lower than 0. So this would show us that the first population mean is statistically lower than the second population mean based on our sample. Our alpha, or level of significance, still goes in the lower tail, and we're still looking for a z critical value that would give us that much area in the lower tail. We would reject the null if our z-score is to the left of this z critical value. The same idea for the right tail. If our two means are so much different from each other that this is some really big positive value, more than this z critical number of standard errors above the mean, we would reject the null hypothesis and be able to accept this alternative. In the two-tail test, we again split the level of significance into the two tails and get these two z critical value cutoffs. If that mean difference is further away than this many standard errors, we can reject the null hypothesis. And that difference could be really small, or it could be really big. Either of those will allow us to reject the null hypothesis. So let's look at an example of this. We don't know the true population standard deviations in this case, but we're assuming that those two things are equal. Based on our sample information, that seems to be a reasonable assumption. So let's suppose you're a financial analyst for a brokerage firm. You want to know if there's a difference in the dividend yield between stocks listed on the New York Stock Exchange and the NASDAQ. Remember, the dividend is the money that you get in a quarterly check or an annual check from a stock that really is just a share of the profits. So suppose you go onto something like Yahoo Finance and you collect some information on the New York Stock Exchange and the NASDAQ. You collect 21 stocks and their dividends, and from that you calculate a sample mean of $3.27 with a standard deviation of 1.3. You collect 25 stocks from the NASDAQ and their yields, and you average that dividend yield together to get an average of $2.53 with a standard deviation of 1.16. We want to know really if $3.27 is statistically different from $2.53. Let's assume a 5% level of significance and test this. Our test statistic is our point estimate minus our hypothesized mean difference divided by our pooled standard deviation. We can use our pooled standard deviation because we have those two sample standard deviations. We don't know the true population standard deviations, and we're assuming that the variances from the two populations are approximately equal. So our point estimate is the New York Stock Exchange value, $3.27, minus the NASDAQ value, $2.53. Our hypothesized mean difference is 0 because that was the difference that we were putting in our null hypothesis. To calculate the pooled standard deviation, we actually have to do the following. 21 observations minus 1 times $1.30 squared plus 25 minus 1 observations times $1.16 squared divided by those degrees of freedom, 21 plus 25 minus 2. That gives us a pooled standard deviation of basically $1.23. We'll multiply that by the square root of 1 over the sample size for each of those samples and add those fractions together. This gives us a test statistic, or a t-score, of 2.040. This is saying that the difference between these two means is 2.04 standard deviations away from 0. Let's see if that's statistically significant. So we're going to test at the 5% level of significance. We need to calculate our degrees of freedom. So 21 plus 25, those were our two sample sizes, minus 2, that gives us 44 degrees of freedom. We can use t.inv.2t, the t-inverse function that gives us a critical value for a two-tailed test, our 5% level of significance and the 44 degrees of freedom, to get this t-critical value of 2.0154. Since this is a two-tailed test, we split that 5% into the two tails. So if we're more than negative 2.0154 standard deviations below, or more than 2.0154 standard deviations above, we can reject the null hypothesis. Our test statistic was 2.04. That means the difference between our sample means is 2 standard errors above 0. We only had to have that difference be 2.015 standard deviations above 0, and we're actually 2.04 standard deviation above 0. So we can reject the null hypothesis and conclude that there's evidence that these means are different from each other. The dividend is different between the two stock indices.